Okay, class. Sorry I can't be in today. I'm just not really feeling the best, but I'll try to do a video lesson. Let's see how this goes. So today's lesson, 4.7, is really dealing about solving quadratic trigonometric equations. All right. So quadratic just means you're going to have terms in there. Your highest order is going to be 2. All right. Whether that be a trig or a regular polynomial, it's order 2. And why is that a special case, and why are we doing an entire lesson on it? Well, look, let's solve this first recap and just see how it differs from the previous one from 4.6. So if I'm solving for x here, again, you're finding a definitive answer. You're telling me like x equals whatever it is. And like that, whatever value you find there, that means when you plug it in here, it will give you this output being 0. So just always keep that in mind when we go about solving these trig equations. Like that's the goal. You're finding a definitive value for x that would satisfy this equation. Meaning that when you get your answer and you plug it back into the original problem, you can do this on a test, you should get the original what you're solving for. So just rearranging this, that's 4x squared is 1, x squared is 1 over 4, and then take the square root of both sides. You would get x is the square root of 1/4. Evaluating that root, you get x is plus or minus 1/2. And is this idea, this plus or minus, that is going to be the focus of today's lesson, all right? So let's apply that same algebra to a trig problem. If we have 4 sine squared x minus 1, isolate it so that way you can solve for x, all right? So 4 sine squared x 1, sine squared x is 1/4. And just as a recap, that's sine squared. That is the same thing as me saying squared up top here, okay? It is not the same thing as me saying sine x squared. Those are not equal to each other. Like this, sorry, let me just kick that horse to death. This sine x squared right here, it means you are evaluating the angle, like you're taking the angle, squaring it, and then using the function sine on it, all right? When you have sine x put to the power 2, it means you're evaluating at the angle x and then squaring whatever your output is. So just understand the difference between the two, okay? All right, so sine x put to 2 equals 1/4. Take the square root of both sides. You're going to get sine x equaling 1 over 2 plus or minus. All right. So the main thing is that your solution can fall in this domain right here. All right. And let's think about what this right here actually means. Sine x equaling positive or minus 1/2. Well, graph sine x. Right? That means right here to here. Well, you're looking for the output of positive or negative 1/2. So like let's say that, you know, well, I mean, not let's say, but this is positive 1 and that would be minus 1. Well, 1/2 is right here. Like that's negative 1/2. Negative 1/2. Half. So you can see that positive. You can see that the positive 1/2 will result in having two solutions right here and here. The negative 1/2 would result in having a solution right here and right here. So by introducing that square root, you're essentially getting double your answers from what we got last time, right? Like, because now you have to evaluate this. You have to evaluate what values of x, when you take the sine of it, would give you the ratio positive 1/2. And you have to evaluate the value of x's, when you take the sine of it, that would give you negative 1/2. Okay, so when looking for values of x that will give you those ratios, you have to think, okay, where is, on this side, where is it positive? Well, sine is positive in quadrant 1 and quadrant 2. And over here, sine is negative in quadrants 3 and quadrant eraser. Quadrants 3 and quadrants 4. And then the second part is what alpha gives you that ratio 1/2, right? So what alpha gives you the ratio where the opposite is 1 and the hypotenuse is 2 in this case because it's a sine ratio? Well, that would have to be pi over 6. So alpha is pi over 6. And because it's the same 1/2 on this side over here, alpha is still just pi over 6. All right, well then your 4 solutions, you can see how they come from. Like you're gonna have a solution there, there, and there. So quadrant 1 solution, and we show it graphically, right? Like you can see, that's quadrant 1. Sorry, my graph's not to scale, but that would be quadrant 2 solution. This one right here would be your quadrant 3. And that one right there would be your quadrant 4. That's like graphical, right? So then in quadrant 1, well, the solution, like x is sine inverse of 1/2. Well, in quadrant 1, that's this x being pi over 6. In quadrant 2, well, now you just have to add, because subtract that alpha from pi, because you're in quadrant 2. So in this case, that would be, 5 pi over 6. So what this means is that these are 2 solutions that would satisfy the above problem. If you were to plug in pi over 6 or 5 pi over 6 into this problem, like pi over 6 or 5 pi over 6, you would get an output of 0, all right? But there's 2 more. Your quadrant 3 is x being pi plus pi over 6. So in that case, that is 7 pi over 6. That's your 3rd solution. And then quadrant 4 solution would be x is 2 pi minus pi over 6. And that would be 12 minus 1, 11 pi over 6. There you go. So these are 4 solutions, and that's for those solutions right above, okay? Like this coordinate right here, so 11 pi over 6 would be that coordinate right there. Like that would line up with that 0. Again, that's what you found, okay? Just always go back to the beginning. Question number 1. Oh, I thought this was 1. Okay, well, anyways, question number 2/1. All right, solve 2 cos squared x plus 3 cos x plus 1 equaling 0 in this domain right here, okay? So what values of x or angles on like essentially the normal unit circle could you plug into these cos ratios here and get an output of 0? Well, we need to solve for x, but this one isn't as easy. It's not like you can like rearrange. All right, I can't just like bring the 1 over here and then isolate for 2. But this looks oddly familiar. This looks like me writing a x squared plus b x plus c, right? Where you have this constant, like plus 1 in this case, where you have this order 1 right here, this order 1, and then you have this order 2 up front, right? It's just essentially looks like a standard quadratic equation. Sorry, a quadratic equation written in standard form. But we just have these cos squared x's up front. Okay, well, let's think, how does this cos squared x come to be? Like, well, cos squared x comes from when you take cos x times cos x. So if we think about that in the context of a quadratic, and that's our first term, well, that means a cos x has to be up front in like the bracket, and there needs to be a cos x here. Well, this 2 is because 2 is there. And then your last term is what goes in the back. Well, 2 numbers that multiply to give positive 1 just has to be positive 1. And you can check, right? Like you can check to see if you just factored that properly. 2 times that cos x right there would give you 2 cos squared x. 2 cos x times that 1 right there gives you 2 cos x. 1 times this x right here would give you cos x. And then 1 times that 1 right there gives you 1. So you get 2 cos squared x plus 3 cos x plus 1. Perfect. So you factored it properly. So this is now the problem that we're dealing with. We are saying, okay, well, 2 cos x plus 1 cos x plus 1. When does that equal 0? Well, just like you did in grade 10, you take your factors and you say, okay, well, when does this factor, this cos x plus 1, when does that one equal 0? And then you do the same thing over here. You say, okay, well, when does this factor? When does cos x plus 1? When does this one equal 0? And now, like, imagine these problems being, like independent. Imagine I just gave you this as a question, right? Well, it's pretty easy to solve, right? And if we look back to our domain, we're looking for values of x that would satisfy this, like, this problem right here on this side. So rearrange. That's cos x being 1/2. Well, 2 parts to that, right? Part 1 is saying when is it negative? Well, cos is negative in quadrant 2 and quadrant 3. And when is like, what alpha would give me that ratio? Well, that ratio would then have to be pi over 3, right? Like your triangle. Pi over 3 would result in this being 1 and this being 2. And if we solve that then, so quadrant 2, your solution would be x is pi minus your alpha. So x is pi minus pi over 3, giving you 2 pi over 3. That is one of your solutions. And then your quadrant 3 solution would be x is pi plus alpha. So then x is pi plus pi over 3, giving you x of 4 pi over 3. Perfect. And then you just have the other side over here. So you've found 2 solutions to your overall problem, but then you have this side. So rearrange. Cos x is minus 1. All right, well, this one's not, I guess, like as easy because you can see that usually we have this like fraction term right here. But think, what value for x do I have to put in here that would give me this output? Where is cosine negative 1? Well, cosine looks like this. And in the 0 to 2 pi domain, you have one area right here which would give you solution of negative 1. That occurs right here at pi. So in this quadrant, you don't even have to do the whole quadrant and acute angle type thing. You can just simply say cosine inverse negative 1. X has to be only equal to one solution on this side because there's only one solution in your 0 to 2 pi domain that can result in a cosine having a value of negative 1. So I should have done this above, but like really what you've just found, okay, so like if you want to write a therefore statement, right, like therefore there is 3 solutions to 2 cos squared x plus 3 cos x plus 1. There are 3 solutions that would give a value of 0, okay? Like, so that means if you were to like plot this on Desmos, you would see that like at these x coordinates right here, your output, your y value would be 0. That's what you just found. Okay. Question 2. 3 sine x plus 2 cos double angle x equals 2 in the 0 to 2 pi domain. So we're looking for values of x that would give the output of being 2 in that domain. Well, first of all, that equaling 2, that's a problem, all right? Like we're dealing with solve solutions, like we always want a 0 on that side. So let's bring that over. 3 sine x plus 2 cos 2x minus 2. Let's set that equals 0. Okay, cool. Well, the other problem I see here is like this double angle right here. Like I have no idea how to solve this with this double angle. So I'm going to use one of my 3 cos double angle identities to get rid of that. And now, which one would make sense to use? Well, in this case, because we have a sine up front here, I probably want to have my whole equation with the same trig ratio. So the one I'm going to use, like I'm not going to use cosine squared x minus sine squared x, because I'd have a cos squared in there, and that would make it even more complicated. That would make it even more complicated. So the one that would make sense to use would really just be the 1 minus the sine squared x minus 2, because now you only have one type of trig equation or trig function in there. Like look back to what we've done, right? Like there's only cosines in here. There's only sines in here. So try to use your identities when given something that looks like this. Use your identities to get it written in terms of just one trig function. All right, so we've satisfied the 0 on the back. We've got rid of the cosine double angle. Now let's just clean it up a bit. So 3 sine x plus 2 minus 2 sine squared x minus 2 in the back equaling 0. Well, I see I have a positive 2 and a negative 2, so let's cancel those. Oh, sorry. Oh, this should actually be a double angle, right? Sorry, I made a mistake. This is 1 minus 2 sine x. There we go. So that would make that one 4 right there. Okay. So 3 sine x. So then you simplify that further. Sine x minus 4 sine squared x equaling 0. All right. Well, just as we've done before, you're trying to find the values of x that would make this equal to 0. All right. So you need to factor it. Well, I see I have a common factor inside of my 2 terms, so let me pull that sine x out, and that would result in 3 minus 4 sine x, again, still equals 0. So now you have your 2 factors, so evaluate them independently. So you have this side, where you need to evaluate sine x, where that one is 0, and you need to evaluate the side right here. When is 3 minus 4 sine x equal to 0? All right, well, I mean, we're still in the 0 to 2 pi domain, so if you think about a sine graph right over here, right, you're going to have 3 solutions for when it's equal to 0, right on the x-axis. So what values of x, if you rearrange, what values for x in this domain give you 0? Well, that means x could be 0, pi, or 2 pi. Where is sine 0? So this one actually gives you 3 solutions. And this side right over here, well, let's rearrange for sine x again. So that would be, bring the 3 over minus 4, that would be 3 over 4. So in this case, we're looking for values of x that would give us 3 over 4. Well, 1, it's positive, so that means we're going to have a solution for x in quadrants 1 and quadrants 2. And the second part is what alpha gives us that ratio of 3 over 4. Well, 3 over 4 isn't a special angle. It's not 1/2, it's not root 3 over 2, it's not root 2 over 2. So it's not going to be a nice number. So if you take the inverse of 3 over 4, you will get, let me see, sine inverse 3 divided by 4. That is going to give you an alpha of 0.85. I'm going to rough because we had a round. Okay. So just as we've done before, now you get your solutions. Your solutions are going to be in quadrant 1. All right, that is going to be, well, x is just equal to alpha in quadrant 1. So x is 0.85. And then quadrant 2, x is equal to pi minus alpha, 0.85. And again, that's not going to be a nice number because you're dealing with a decimal here. So pi minus 0.85, I get roughly 2.29. And there are more. So again, like a therefore statement. So therefore, there are 5 solutions in this case. 5 solutions that would make, what's our original problem? 3 sine x plus 2 cos 2x equal to 2. All right, like that's what you just found. All right, problem number 3. Sine squared x minus cos x squared x equaling 0, but our domain's different. 2 pi, 4 pi. So let's first talk about this domain. All right, like what does this mean to you? Well, this is always your lower bound, like the one that's on the left-hand side in 4 pi. So usually our domain is 0 and 2 pi, right? It's just you going around one pass around the unit circle. Well, what happens if you went around a second time? Well, if you went around a second time, you'd actually go 4 pi, right? So what this is saying, what this domain is telling you is, okay, well, I know this is a lot more complicated of a function, but like let's say you had a graph of that. Like let's say you graphed this function right here, and it looks something like this, okay? It's a trig function. All right, so let's say it looks something like that. Well, what I'm asking you to do is like, if usually it's 0 to 2 pi, well, I'm just asking you to look at it from the second half of the domain. I'm asking you to look from 2 pi to 4 pi. So I'm asking you just to evaluate, get your solutions in this domain. These are the thetas, like all the thetas, all the possible x values happen in this domain right here, not in the other one, right? So when you think of your axes, like your unit circle, you really have to think of it at starting at 2 pi, you know, and like if let's say you went around halfway, you would end up here at 3 pi. And let's say you went around again, you would end up back at 4 pi, right? So all of our alphas and stuff, like let's say we have something that falls into this quadrant right here. Well, really, like if that's alpha, when you go to evaluate that quadrant, like that quadrant 2 in this case really is actually you saying 3 pi minus that alpha, right? Because that's really now the 3 pi axis, because you're looking in this domain here. So just keep that in mind when we're going through solving this, all right? Like when we start evaluating our quadrants. Okay, well, I mean, also we need this looks pretty complicated. This isn't just simply like factor it or anything like that, because you now have a sine and a cos. So as we did in the previous one, let's get rid of it. Let's somehow only have one type of trig function. So the way my brain sees this is, oh, okay, I see that I can probably turn this right here into a tan function. If I write, actually there's multiple ways because you can use the Pythagorean identity too. But let me show you option number 1 then. I see this as me saying sine squared x minus cos squared x, cos squared x equaling 0. Well, if I bring the cosine over to the other side, so if I make that positive cos x, and then if I divide both by cos squared x, right? Well, now I have one trig function. I've rewritten the original problem as like you're solving for x when tan squared is equal to 1, right? Like this and this are equal to each other. They're equal to each other. It's the same problem. All right, well, evaluate. So that means take the square root, both sides. You're going to find when tan x is positive or negative 1. All right. Well, think, what does that mean? Like first of all, you have the two camps. You have tan x equaling positive 1, and you have the other camp right over here, where you have where is the values of x that would give that to be a negative 1. So you're looking for the values of x that would be positive 1 or negative 1. Well, tan is the ratio. Tan of some angle x is the ratio of opposite over adjacent. So because we have a value of 1, that means the opposite and the adjacent are also 1. Or not 1, but like the same value, because whatever's on top by whatever's on the bottom. So what triangle has opposite and adjacent having the same value? Well, it's the pi over 4 triangle. All right? So that's going to be our related acute angle for both of these. Like step 2, both of these are going to have an alpha of pi over 4 because it's where tan is 1. All right, but this one is positive, so that means tan is positive in quadrants 1 and quadrants 3. And this one is quadrant 2 and quadrant 4. So now solving it, get your quadrant 1 solution, okay? But again, keep in mind your domain, okay? So usually it's just x is equal to alpha if it was 0 to 2 pi. But because we start at 2 pi and we go all the way to 4 pi, well, now you start your quadrant 1 solution is really 2 pi plus that alpha. Okay, so then your x is 2 pi plus pi over 4. All right. So actually, let me just make a nice little arrow there. Okay. So then your first solution is what? That'd be 9 pi over 4. Perfect. That's one solution. And then your other one would be in quadrant 3. So x in this case, because it's quadrant 3, would be in our quadrant 3, go back to this new unit circle we've drawn, is 3 pi. So that means quadrant 3 is 3 pi plus alpha. So that would be 3 pi plus pi over 4. And that would result in 13 pi over 4. I wrote those really big, but let me reduce that. Okay. And then over here, your quadrant 2 solution would be, in quadrant 2, x is 3 pi minus that pi over 4. So that would be 12 minus 1, so that would be 11 pi over 4. There is your third solution. And then your quadrant 4 solution would be x is now 4 pi minus pi over 4. So that's x is 15 pi over 4. There you go. And I was saying, like I saw this as turning it into the tan ratio right here, but you could have also approached this problem by using the Pythagorean identity. Like you would have got the same solution. So what I mean is, like, if you went from the very beginning, if you saw this as like option number 2, if you saw sine squared x minus cos squared x, and you saw, okay, well, I'm so used to seeing whenever, like, you listen to me in class, say, okay, I see sine squared, I see cos squared, I think Pythagorean. Well, you could have turned this right here into 1 minus cos squared x, because now you only have cosines in the problem, right? And you would have got 1 minus 2 cos squared x equaling 0. So if you were to rearrange this problem, so bring the 1 over, the 2 over, cos squared x equaling 1 over 2, and then you take the square root of both sides, you get cos x is 1 over root 2, which is the same thing as root 2 over 2. Okay, well, what alpha, all right, like look, oh, sorry, because you took a root, positive, negative. Well, what alpha would give you root 2 over 2? Well, in option 2, you're still going to have the same alpha. It's still going to be pi over 4. So that means whenever you do all of your quadrants, like when you evaluate, oh, and I skipped this up, and where is it positive and where is it negative? Well, that means you're going to also have 4 different solutions, right? Because cosine is positive in 1 and 3. Like it's positive in quadrants 1 and quadrant 4. And it's negative in quadrant 3, or 2, and quadrant 3. All right. And then your alpha is going to be pi over 4 in both ones. And look, like that's the same thing you just did here. Quadrant 1, quadrant 3, quadrant 2, quadrant 4, and using the same alpha. Like all of your quadrant evaluations here, all of these are just going to be using the same things we did here, where you're going to take your solution in quadrant 2 is going to be 3 pi minus that pi over 4. Quadrant 4 is going to be 4 pi minus that pi over 4. So you're going to get the same solution here. Like if you go through all the steps, you're going to get the exact same x values that you just got right here. So sorry if that was loud in your headphones. Okay. Yeah, so like you could have approached that with the Pythagorean identity and you would have got the same solution. So it's okay. Like whatever one worked for you, that works. And number 4, last one, I think. Yes, last one. Solve 2 cosecant squared x plus cosecant x minus 1. Well, again, this looks very familiar to ax squared plus bx plus c equals 0. So, like if it helps you like to think of like this right here and make it easier for you to like see how to factor it, you can easily go like let z equal cosecant x, for example, okay? So wherever there's a cosecant x, you're just going to put it as z. That would be 2z squared plus z minus 1. So imagine I turned this into that, right? Like now that's way, way easier to factor. So that would be 2z. That would have to be the minus 1 here, and then that one would have to be the positive. Okay? Like that was so much quicker. Well, now just go back and replace the z's with the cosecants. So that would be 2 cosecant x minus 1 cosecant x plus 1 equals 0. And now it's like everything we've done. We take this factor and you evaluate it when it's 0. So 2 cosecant x minus 1. And you take this factor and you evaluate it. What value of x would result in this one? Oh, I wrote cos. That should be cosecant. There we go. Plus 1 is 0. All right, let's do the left-hand side. So rearranging this equaling 0. Well, just lots of mistakes. All right, so bring the negative 1 over and the 2. So you'd be cosecant x being 1/2. Well, I don't have a cosecant button on my calculator. All right, so really just turn that back into sine. So cosecant is the same thing as 1 over sine x. So I can write that as like me saying 1 over sine x is equal to 1/2. Well, I want what sine x is equal to, not 1 over sine x. So just flip both your fractions. All right, so that would be the same thing as me saying sine x over 1 is equal to 2 over 1. All right, you just flip both your fractions. So both things divided by 1, just you can get rid of those. So really it's sine x is equal to 2. Okay, so what value of x would give you a ratio of 2? Well, that's not possible. You can't. There is no value for x that would give you a ratio of 2. Because what does this mean right here? Well, that 2 means that's like me saying again like 2 over 1. That means you would have a triangle that would have an opposite of 2 and a hypotenuse of 1. But that's not possible because hypotenuse, by definition, needs to be bigger than the opposite. So not possible, or no solution. No solution. On that factor, at least. All right, this one might have a factor. This one might have a solution. So if we evaluate the right-hand side, so let's just do our math over here. So cosecant x plus 1 equaling 0. So that would be cosecant x being minus 1. So then same approach we did last time, 1 over sine x is the same thing as me saying negative 1 over 1. So sine x is negative 1. Okay, well what value of x would result in you getting a negative 1 for sine? All right, well, what domain are we doing this? I forgot. 0 to 2 pi. Okay, well, in the 0 to 2 pi domain, all right, well, there's only one value that would result in sine having an output of -1, and that occurs right here at 3 pi over 2. So that's x is 3 pi over 2. So really, there is only one solution to this problem. So that means if you were to graph this on Desmos, right, and you would see that the 2 cosecant squared x, actually it's already there for a statement. Therefore, there is one solution to 2 cosecant squared x plus cosecant x minus 1. All right, there's one solution to this where it equals to 0, because it was 0 here. So always think back to like what it is, like the problem at hand, what you're solving for, right? Okay, cool. If you have any questions about this lesson, just send me an email, all right? And I'll see you on Tuesday. Take care.